All right. Hi, guys. Gonna finish the very last video for the nuclear chem packet. So I left off at question 48. So I'm just gonna start there and I'm just gonna do 48 through 71 in one shot. Okay. I'm gonna try and kind of go as fast as I can. But you do have the option to slow down videos on YouTube. So if you need to do that, please take advantage of that feature. Anyways, number 48. Which isotope is used to treat cancer? So this comes from lesson 5.7 where we spoke about the radioactive applications. So this really is just a thing that has to be committed to memory, okay? But let's just go through each one. So my pen, what color shall we do today? Feeling pink. Let's go with pink. Yeah, pink sounds good. There we go. Okay. So C14, this is used for dating things, how old they are. This can be used for things about 40,000 to 60,000 years old. It's only got a half-life of 5,700 years. So if you need to date something that is older than carbon-14, you got to use something that has a longer half-life. Cobalt-60, this is the answer to our question. This is something that we use to treat cancer radiation therapy. Okay. U-238 and lead-206. We use both of these. We use the ratio between these things to basically date I don't know how to geological, yes, English. Date geological objects, things like rocks or things like that. Uranium has a really, really long half-life. So this is good to date something like that. So yeah, our answer would be choice C for this one. Also, giving a little shout out to some of my students in period 10 because they specifically asked for a shout out. So, hi guys. All right, 49. So, which net change occurs in both nuclear fission and fusion? So, the same goes for both of them. Okay. And we spoke about this in lesson 5.5, I believe. So, we use this equation to describe what's going on here. Again, we didn't learn how to use the equation. I just kind of introduced you to the idea of it. When we're talking about both fission and fusion reactions, we actually do lose a little mass. So our products always have a little bit of a smaller mass than the reactants, okay, which does violate the law of conservation of matter or mass. But we actually do take some of the mass from our reactants and it actually gets converted right into energy. And this goes for both of them. Okay. So this will always go for both fission and fusion. Alrighty. Mouse back. Okey dokes. Number 50. So this kind of goes back into what we were just saying. So in a nuclear fusion reaction, the mass of the products, okay, now again, although you're taking two lighter things, right, something like hydrogen and some other form of hydrogen, and you combine them usually to make helium, although you're taking two lighter things and combining them to make one thing that is heavier, okay, this product is going to have a mass that is very slightly lower than both of these things combined. So even though you are combining these to make one thing that is heavier than each of them individually, the overall product still weighs less than both of the reactants put together. So for this one, we want to go with choice A. Okay, so the mass of the products is less than the mass of the reactants because we do take some of that mass and we actually convert it to energy. And again, this goes for both fission and fusion. All right, number 51. The ratio of the mass of U-238 to the mass of Pb-206 can be used too, and we actually just went over this one in, I think, question 48. This one would be to date geological formations, okay? So like mountains or rocks or something of that nature. Alrighty. And again, this is just a memorization sort of thing here. And again, you can find all that information from your guided notes in lesson 5.7. There's also a specific video for that lesson and for all of the other lessons on the website under the exam reviews. Okay. 52. Another question about radioisotopes. So which procedure is based on the half-life of a radioisotope? So it's not A, not B. B is that is cobalt 60, what we spoke about before. Counting to determining level of radioactivity. No. Dating to determine age is something that we would need to know the half-life for. So something like C14, again, we need to, when we want to date how old something is, we need radioisotopes that have very long half-lives. Now, the most common one is C14. But if you need something, again, if you need to date something that is older than about 60,000 years, you got to use a different radioisotope that has a longer half-life. All right. Number 53. And I just went over this one, actually. Just said it. So which isotope is most commonly used in the radioactive dating of the remains of organic materials? Organic means that it came from something that was once living. And this, again, would be C14. Okay. 54. We also just went over this. This is like, there's some of the questions are like very repetitive. So they like to ask the same sorts of questions. They just reword them depending on like what year the region comes out, like the year of the region, I mean. 54. So a radioactive dating procedure to determine the age of a mineral, so this is the geological formation, compares the mineral's remaining amounts of isotope U-238 and isotope lead-206. Okay. So again, it is the ratio between these two isotopes that will allow scientists to tell how old some sort of geological formation is. 55. Which radioisotope is used to diagnose thyroid disorders? And this one would be iodine-131. Again, this is all just memorization. And this comes right from 5.7. We're already on the next page. Okay. This is a very good question and also kind of shows us that whole thing with mass being converted to energy. Okay. Because all these numbers here, like all these mass numbers and everything that you see, all that is rounded. Right? These things don't, exist in these nice whole numbers. Their masses are usually long decimals, okay? And now we can actually see the total mass of the reactants versus the product side. Again, this is the reactant side. That does not look like an R. That looks like a person now. Okay, that's the reactant side, and this is our product side. And we can see here that the total mass of our reactants is 236.053 EU or AMU. And here, the total mass of our products is slightly less. Okay. Again, this got rounded, this 8 here rounded this whole thing up to an even 236. And this, because this first decimal is a 0, this whole thing got rounded down to 236. So it would seem that the atomic masses on each side are exactly the same. However, there is a small difference. And we actually lost mass. Again, where did that mass go? That mass got converted into energy. All right, so we can eliminate the first two because mass is not gained, our mass went down. And where did the mass go? It turned into energy. So if we look at C, mass is lost due to the conversion of mass to energy. So we want to go with C. D doesn't make sense because you're saying mass is lost due to the conversion of energy to mass. If you're converting something to mass, then you're gaining energy. So this sentence just doesn't even make any sense. So our answer would be choice C. All right. All right, I think we got a few more multiple choice, and then we'll start with the short answer. Alrighty, 57. A radioisotope is called a tracer when it is used to, again, we want to use tracers to trace something or to follow something, okay? Not used to kill bacteria in food, not used to kill cancerous tissue, not used to determine the age of an animal's skeletal remains. This is, again, to follow the pathway of some sort of chemical reaction. We use this very commonly in medicine to track some sort of bodily function that is occurring, okay? So choice D. 58. Which type of reaction produces energy and intensely radioactive waste products? So energy and something that's radioactive is going to come from some sort of nuclear reaction. Burning of heat, of heating oil and burning of wood, those are both chemical reactions. it's really between fission and fusion. Okay, and when we remember which one produces radioactive waste, that one is fission. Okay, and again, this is why we are really concerned and really we really want to be able to have fusion reactors instead of fission reactors, because fusion reactions don't produce any radioactive waste. Fission does. Okey-doke. 59. One benefit of nuclear fission reactions is, so choice A, nuclear reactor meltdowns. This is not a benefit. This is a terrible thing. Okay. So this is when something goes just absolutely wrong in a nuclear power plant. Okay. Similar to Chernobyl. Benefit of nuclear fission, storage of waste materials. This is not a benefit. Having to store radioactive waste materials is not a good thing. It poses a big problem for nuclear fission. Okay. Biological exposure. You don't want to be exposed to anything that is radioactive. So this is the opposite of a benefit. This is a risk. The one benefit of nuclear fission is that it produces a ton of energy, way more than the burning of fossil fuels or any other energy source that we currently have. The only thing better than fission in terms of how much energy is produced would be fusion. Again, but it's very difficult to get those conditions that you need in order to get fusion to occur on Earth. Number 60. Which phrase describes a risk associated with producing energy in a nuclear power plant? So we are looking for a risk now, not a benefit. Okay. Depletion of atmospheric hydrogen. This has nothing to do with it. Depletion of atmospheric carbon dioxide. Again, nothing to do with it. Production of wastes needing long-term storage. This is definitely a risk. You don't want to put this stuff near anything alive, or you don't want to contaminate an ecosystem or have people exposed to any of this stuff. So this is definitely a risk. Okay. Production of waste that cools surrounding water supplies. You don't want to put any of this waste into any sort of water supply. So this doesn't even make any sense. All right. So our choice would be C. 61. Which phrase describes a risk of using the radioisotope cobalt-60 in treating cancer? So we can use cobalt-60 to treat cancer, as that's radiation therapy. Not the only type of thing that we use to treat radiation, not the only type of isotope that we use in radiation treatment, sorry. But it is one of the common ones. Now you can get overexposed to this, okay? But in small amounts and focus on one particular part of the body, it does more good than bad. So let's look. A, production of acid rain. That has absolutely nothing to do with it. Production of greenhouse gases. Again, absolutely nothing to do with it. Increased biological exposure. Again, you are literally radiating someone's body, a particular part, okay? You can over-radiate someone, and this can get them sick, okay? This can cause lots of biological problems. So you do run the risk of overexposure, okay? You don't want too much radiation. So this would be the choice that we would want to go with. Increased ozone depletion, the ozone layer. This has nothing to do with the ozone layer. All right. Okie dokes. I think we are now moving on, yes, to the short response. Perfect. Okay. Now again, remember, a lot of times in a lot of the short response questions, they give you information that is absolutely irrelevant. Okay. So they give you all this information about all these isotopes of UUS, 239, 293, 294, how it's made. We don't care about any of this. Okay. They even give us the half-life of this thing, and they ask us absolutely nothing about berkelium, BK. Okay. So most of this is just garbage information. We don't actually need it. So all they're actually asking us to do is just complete the following nuclear equation. That's all you got to do. All you need is a periodic table. Okay. However, even though some of this stuff is irrelevant, still please make sure that you read the entire question and all of the text completely. Okay. You have to determine what is necessary to answer the question and what is irrelevant. In order to make that distinction, you got to read the entire thing very carefully. Okay. So don't just skip reading stuff. Now, So they want us to complete this alpha decay for US 294. And again, this is like any other equation, like in math, okay? Both sides of the equation have to be equal. Our equal sign in chemistry is basically this arrow, okay? So both of these sides have to be equal. Now on the bottom, right here, this is our atomic number. They have to summate to each other on each side. So the total atomic number on the reactant side is 117. Also needs to be 117 on the product side. Right now it's only 2. So what do we got to add to 2 to get to 117? That's 115. And we have to also balance the mass number. Mass number on this side, 294. Over here, it's just 4. What do I got to add to 4 to get 294? That would be 290. Okay, this is the most important information that I need in order to determine what element we have become. So we're going to go over here to our reference table. Ignore the markings for just a moment. So I need to see what is element 115, and that is UUP. So right here, I'm going to add in my new element, UUP. The second U should be lowercase. Let me rewrite that. U. Alrighty. So this would be our final equation. Okay. Again, this is an alpha decay. This is also a natural transmutation. Again, remember natural transmutations only have one reactant. All right. If it's artificial, the clue is that it will have 2 reactants. Okay. Number 63. So they give us all this information for both 63 and 64. Okay. I'm not going to read this, but you can read this on your own. Anyway, 63, they're asking what fraction of an original, and they're talking about this one, of an original radium-228 sample remains unchanged after 17.4 years. Now, whenever you see a question about half-life and they're asking, and they say this word fraction, okay, it doesn't matter how much you start with, okay? No matter what amount of something you start with, and no matter what the isotope is, after one half-life, regardless of what you started with, you're going to have half of what you first had. After another half-life, you're going to have a quarter. And this is going to keep going on and on and on. So what I want to do is I want to figure out how many half-life periods are happening. Again, remember that the equation, and you don't have to use it because you can just use kind of like logic. But if you'd rather use the equation, that's perfectly fine. This is our equation. So again, half-life equals the time elapsed over the half-life periods. So I want to know how many half-life periods are happening, okay? So this is my time elapsed right here. So I'll erase this. This is 17.4. The number of half-life periods is what I'm trying to figure out. So this is just, X. The half-life of radium-228 is 5.8 years. By the way, I know it's years because right here in the top of the column, it says Y. That stands for years. Anyways, 5.8. And now all you got to do is just cross multiply. If it makes you feel more comfortable, you just put this over 1. What you really end up doing is doing 17.4 divided by 5.8, and this comes out to 3. This means that this thing has gone through 3 half-lives in a matter of 17.4 years. So that's an important bit of information that I need to know. Now, again, like I said, it does not matter at all how much you start off with, okay? Let's just say we start off with 1 gram, okay? After 1 half-life, and I don't even care how long it is, this goes for any isotope, okay? But for this one, we're specifically going through 3 half-lives. After 1 half-life, I have 0.5, or basically I have 1/2 of what I started with. After another, I'll have 0.25. This is a quarter of what I started with. And after a third, I will have 0.125. This is 1/8 of what I started with. And it doesn't matter if you made this number 100, it doesn't matter if you made it 57,000. After 3 half-lives, you'll only have always 1/8 of what you started with. So the answer for this one is 1/8. Okay. Alrighty, next one. Complete the nuclear equation below for the beta decay. of PM 147 by writing an isotope notation for the missing product. So let me just zoom in. All right. So we can see the beta particle right here on the product side. By the way, if this were on the reactant side, this would be electron capture, but they really don't ask about electron capture. You'll mostly see beta decay, alpha decay. Usually you'll see that. Anyways, beta decay. So we've got, again, PM 61. So our total atomic number on this side is 61. Right now on this side, it's -1. So what do I have to add to -1 to get 61? Well, I have to add 62. 62 plus -1 is 61. So now everything balances. Again, if you're not comfortable with the positive and negatives, just use a calculator. And again, remember, everything on this side has to equal everything on this side added up. So again, 62 plus -1 is 61, okay? Total mass number on the reactant side is 147. On the product side, it's 0. So what do I got to add to 0? Obviously, I have to add 147. Now, again, this number at the bottom, the atomic number, is the important number that I need. That is going to determine what element we have become after this thing has gone through beta decay. So I'm going to go over here. I'm going to find element 62, and it is right here, SM. Okay, so that is my new nuclide, SM. That is my final answer. Okay. Alrighty. Go. Come on. Okay. 65. So iodine has many isotopes, but only iodine 127 is stable and is found in nature. One radioactive isotope, iodine 108, decays by alpha particle emission. Iodine 131 is also radioactive and has many important medical uses. Then you can see that they're asking us about iodine 131. So that means that most of this is not needed. Okay. So they're telling us that the total time required, or they're asking us to find the total time required to go from an 80-gram sample to a 1.25 gram sample of iodine 131. Okay, so first thing I want to do is I'm just going to go over to my reference table, and I want to know how long is the half-life for iodine 131. I know it's sideways. It's 8.0121 days. So I'll write that over here. I'm just going to write that on the side here. Half-life is 8.021 days, and I'll come back to this information. Now, they're giving us the starting amount and a finishing amount. Okay, we've gone from 80 grams down to 125. How many times did this thing have to decay to go from 80 to only 1.25? Again, this is the number of half-life periods. So let's test it out. 80. After one half-life period, we've got 40. After another 20, another 10, another 5, another 2.5, and another 1.25. And again, count your arrows. I'm going to just change the color for a moment. We're going to do some green. So we've got one half-life period. Again, count your arrows. 1, 2, 3, 4, 5, and 6. So we decayed 6 times. Okay. So we decayed 6 times, and each half-life takes 8.021 days. And we did this 6 times, so you just multiply them. This comes out to about 48 days. There is a decimal, but you can round to 48. You can also round to, I think, 48.1 it comes out to. But 48 is good enough. Anywho. Excusez-moi. Lots of talking. Lots of talking. Alrighty. We're almost done. 66. Another half-life problem. So they give you all this information, okay? And then their final thing that they say is determine the total time that must elapse until only 1/16 of an original sample of thorium-234 remains unchanged. Now, again, they're talking about a fraction, okay? So again, it doesn't really matter what amount we start with. You can start with 1 gram, you can start with 23 grams, it doesn't matter. Okay, we're just going to go ahead and say we're going to start with 1 gram. And I'm going to do this up here because there's a little bit more room. Let's say we start off with 1 gram. After one half-life, which by the way for thorium-234 is about 24 days. After 24 days, 1 gram would turn into 0.5 grams. This is also 1/2. You can rewrite it like that. After another half-life, so after another 24 days, we've only got 0.25. This is 1/4 of what we originally started with. After another, we've got 0.125. This is 1/8 of what we started with. After another, then we have 0.0625 grams. This is 1/16. So you can see that you're just constantly multiplying these numbers by 2. That's how you get fraction. Okay. So this took, let me change my color again. Let's do orange. So this took 1, 2, 3, 4. 4 half-life periods, and each half-life period is 24.10 days. So it's just 4 times 24.10. And this comes out to be 96.40 days. This is how long this would take. Okay. All right. All right, number 67. Base your answer to the following question on the info that they give you below. Okay. They give you all this information, and then they just ask you to do this. Okay. Again, make sure that you read the information anyways. Sometimes there is plenty of useful stuff in it. But for this one, this is all we need. We just need to figure out this equation. We just need to write the nuclear equation. Okay, so we have polonium-218 undergoing some sort of change to become lead-214. So we want to figure out what particle is this thing going to emit. Again, you want to make sure that everything is balanced on both sides. Our mass number over here on the reactant side is 218. On the product side, it's 214. So what do we got to add to 214 to get 218? Well, I have to add 4. On this side, atomic number is 84. On this side, it's only 82. What do I got to add to 82 to make it 84? Well, I have to add it 2. And I know just right off the bat, looking at this is going to be an alpha particle. So this thing went through alpha decay. Again, you can write it like this, or you can write it like this. It doesn't matter which way you do it. Okay. And again, if you can't remember which particle has a mass of 4 and a atomic number or charge of 2, just go to table O. It tells you all of the particles. Okay. 68, another nuclear equation that you have to write. Okay, so they give you all this information, and then they just want you to write the nuclear equation. So we've got technetium-99. We want to know what sort of particle got spit out by MO99. Again, on this side, I've got 42 as my atomic number. On this side, I've got 43. So how do I basically bring the 43 down to 42? This must be a -1. And the mass hasn't changed. So this is just a 0. So what particle has no mass and a charge of -1? This is a beta particle. The other way that you could have written this is like this. And both will suffice. Both are equally acceptable. Again, a beta particle is basically just a fast-moving electron. Okay. 69. Base your answer, they always say this, to the following question and use the information below. Okay. So they give us this fission equation. Okay, we take uranium-235, break it up into xenon and strontium. They also give us this information about half-life. And then what they ask is to explain in terms of both reactants and products why the reaction represented by the nuclear equation is a fission reaction. Okay, so one thing that you can say, and I'll write this out, one thing that you can say is just that the uranium-235 nucleus splits into smaller nuclei. We take one big thing here and we break it up into 2 smaller or lighter nuclei. Okay, so I'll write this down. So one thing that we could say is the uranium-235 nucleus splits into smaller nuclei. Okay. Another thing that you can possibly say is that one large atom, and when we say this, we're talking about the reactants, is broken down into smaller atoms. And this is also acceptable. So you take one heavy thing and you break it down into smaller atoms. So either of these would be appropriate answer for this question. Okay, 70, question 70. We're almost done. They give you this information. So some things that are used in fission, some things that are used in fusion. And then they're asking, say, one potential benefit of using nuclear fusion instead of the current use of nuclear fission to produce electricity. So a few things that you can say. So for this, one thing that you could say would be that with fusion, okay, there is no waste, or more specifically, no radioactive waste. That's probably the best benefit that we would have. Another benefit is that fusion makes more energy, produces more energy than a fission reaction does. Another thing is that the materials that you need for fusion are way more available. So reactants are more available. So it's easier to get hydrogen than it is to get uranium. So literally the products that we need for fusion are easier to get than the things that we need to get fission to work, sorry. So any of these three answers would be acceptable for this, all right? All right, and finally, our last question. So they give you all of this information. You guys can go on ahead and read it. But we've spoken about this. State one risk or danger associated with radioactivity. You can have a few answers. For one, okay, people can get sick. Or they can get cancer. Or radiation poisoning. Okay. Also, you can contaminate the environment, which you don't want to do. You can contaminate an environment or an ecosystem, and these are not things that you want to do. These are both risks of any sort of radioactivity. Okay. So guys, that is it. I really hope that these videos helped. If you want more information about each topic, again, you can go to the website, my website. You can go under exam reviews and you can take a look at all of the videos that I have linked. I have linked for you a video for every single lesson that we have done, 5.1 through 5.7. Some lessons I've posted 2 videos that I just grabbed from YouTube. If you don't like those, just go to YouTube and type in the topic and a bunch of stuff will come up. But anyways, I hope this was really helpful and I wish you guys the best of luck on your exam. And in the future, you might want to revisit this video too when it's time to start studying for the reagent. Anyways, good luck, guys.